There's another situation where we might find that feedback would help us, or at least might hold out the hope for helping us. Suppose we have a system that includes a nonlinearity, and in particular, a nonlinearity in the forward path. Now, we said that feedback can be used to desensitize us to variations in forward path gain. We can look at nonlinearity as a variation in forward path gain that's dependent on signal level. That's what we mean by a nonlinearity. If we have at least a nonlinearity without energy storage, we find that that's simply an element whose gain is proportional to signal level. Because, or if that nonlinearity is applied in the forward path or is located in the forward path of a feedback system, we might anticipate that the desensitivity associated with feedback systems would tend to moderate the effects of the nonlinearity. And I'd like to look at a system with that characteristic. Here we again have our input, the output. Notice I've changed notation. I have the lowercase variable, the capital subscript, which is a total variable, and I can represent relationships in a nonlinear system that way. The earlier block diagram was a linear one. We have the input. We measure the output and scale it by a factor f of 0.1. Clearly the objective here is to build an amplifier whose closed-loop gain is 10. The ideal relationship between the output and the input, providing the loop transmission magnitude is large enough, would be 1 over f. We'd get an output that's 10 times the input. We then, in the forward path, have an amplifier that provides a gain of 1,000, let's say, and then a nonlinear element. And that completes the forward path. So here we have a nonlinear amplifier in a forward path and a linear feedback element. For purposes of analysis, let's assume some characteristics associated with the nonlinear element that are like this. We have a dead zone. In other words, the input to the nonlinearity, shown on this axis, has to reach 1 volt before the output of the nonlinearity begins to change. That dead zone is typical, for example, of many power handling stages. Again, let me draw an analogy between this system and a power audio amplifier. One very common topology for an audio amplifier involves a complementary emitter-follower, a push-pull pair of emitter-followers using a PNP and an NPN transistor. That sort of topology has very nice characteristics in terms of maximum power output versus quiescent power consumption and that sort of thing. And so a very popular topology for a high-power amplifier involves this sort of complementary emitter-follower. But at least in the simplest versions of that circuit, there's a crossover problem. In particular, what one has to do is exceed the forward threshold of the transistor's approximately 0.6 of a volt in order to get the output to change. And that's the sort of characteristic we've shown here. We imply that there's a region from -1 to +1 for which the output doesn't change. We then go through a region for inputs between 1 and 3 where the slope is 1. We then go through a region of reduced slope. In here, the slope is a 1/10 rather than 1. We go from 3 to 8 on the input, from 2 to 2.5 on the output. And finally, a region where the slope becomes 0, and the nonlinearity is symmetrical. Again, if we were trying to relate this to a power amplifier, we mentioned the crossover distortion. We then get a linear region, a region where the power handling element might be beginning to saturate, and then finally a region where we've reached hard saturation. The output no longer changes in response to the input. In reality, if we look at the characteristics of power handling stages, they aren't quite as abrupt as this, but might curve a bit and do something like so and eventually saturate. So this might be a reasonable approximation to the nonlinear characteristics associated with many power handling stages. We can analyze this particular system fairly easily. In general, the analysis of nonlinear systems is quite challenging, and we'll have more to say about that later in the subject. But this particular one is quite easy, and the reason is that we speculated or hypothesized at the beginning that the forward path had no dynamics, and that gives us an easy way to solve the system. What we can do for this particular one is to look at the various signal levels. We recognize here that the nonlinear element is piecewise linear, and we can assume a value for the output. It's particularly convenient if we assume a value that is at a breakpoint of the nonlinearity. Once we've made that assumption, we're able to determine all of the other signals in the system. We assume a value for the output voltage. Once we know or have assumed that value, of course, we determine VF immediately. The transfer characteristics of the nonlinear element determine VA, the VA that corresponds to that value of VB. Since VA is the output of an amplifier with a linear amplifier with a gain of 1,000, we immediately determine VE, and then we recognize that at this point we have the relationship VI minus VF equals VE, or VI equals VE plus VF. So once we've assumed a value for V out, that pegs VF, the nonlinearity pegs VA, consequently VE. We can determine the value of VI that gives us that value of V out. If we do this for values of V out at the breakpoints, well, we're basically able to connect the dots, follow the dots, and get the overall input to output transfer characteristic for the system. I've indicated the important relationships other than those associated with the nonlinearity for this system. In particular, the fact that the error voltage is simply 10 to the minus third times the voltage at the input to the nonlinearity. That reflects the gain of 1,000 in the forward path. That the relationship at the summing point tells us that the error voltage is the input voltage minus VF, solving for VI so that we can determine the input voltage that ultimately gives rise to a given output. From this equation, we simply get VI is equal to VE plus VF.